Hey everybody. Today we're approximating distance traveled using the subinterval method. This is part of a larger Calc 1 conversation that leads us to the idea of the definite integral. In elementary school, we learned this simple formula, distance equals rate times time, which makes sense when the rate is constant over the interval of time in question. Now, of course, in the real world, rates are frequently not constant, but we can still use this formula to approximate distance even when rates aren't constant, as in this next example. A passenger checks a car's speedometer at 2-minute intervals. At time t equals 2, they see a speed of 34 miles per hour. At time t equals 4, a speed of 30 miles per hour, and so on. Estimate the distance traveled by the car over this 20-minute period. Now, we should not expect to be able to get an exact value here. We have very incomplete information. But we should still be able to get an estimate using this formula up above. The idea is to use the car's speed at the end of each 2-minute interval as an estimate for its speed over that entire interval. So, for example, from t equals 0 to t equals 2, we'll take the car's speed to always be 34 miles per hour, even though we don't know that's exactly the case. Assuming that speed of 34 miles per hour over those first 2 minutes, we can get the distance traveled over those first 2 minutes, at least approximately. Distance is going to be rate times time. Of course, the rate is going to be 34 miles per hour, and the time elapsed is going to be 2 minutes. We have to be a little careful with units here. We have speed in miles per hour, but of course time is being measured in minutes. So we need to convert one of those two to have a common time frame, common time interval. I'll do everything in terms of hours. So instead of 2 minutes, I'll say 2/60ths of an hour. Then the distance traveled in those first 2 minutes is approximately 34 times 2/60ths, or 1.13 miles. Now, we're going to want to repeat this calculation for every 2-minute time interval, and then add up all of the small bits of distance we get to get an approximation for the total distance traveled in those 20 minutes. Here's what we get. Distance equals rate times time plus rate times time plus rate times time, and so on. Here, the time elapsed is always the same, 2/60ths of an hour. So I'm going to factor out that common time interval to write things in a slightly simpler fashion. 2/60ths, the time elapsed, times the sum of all the speeds at the right-hand endpoints of all these different intervals. Simplifying this value, we get 11.1 miles approximately. Okay, let's generalize this procedure. Suppose we know the velocity function v of t of an object. We can estimate the net distance traveled over an interval a less than or equal to t less than or equal to b by breaking up that interval into n equal pieces. If we do that, the width of every piece is going to be b minus a over n, the total time elapsed over the number of pieces we're splitting it into. We're going to want to estimate the velocity over each of those intervals using the right-hand endpoint of each subinterval. So let's write down the right-hand endpoints. It's going to be a plus delta t, a plus 2 delta t, and so on. So start at the left-hand endpoint and move over by the width of an interval, 1 time, then 2 times, then 3 times, and so on until you get to the end. Again, the idea is to estimate the velocity of the object on each subinterval using the right-hand endpoint of that interval. Then the total distance traveled is going to be rate times time plus rate times time plus rate times time, and so on. Again, the time elapsed over each subinterval is always the same, so we can factor that out to get this formula. If we want to write this in sigma notation, we can do so. Sum from k equals 1 to n v of a plus k delta t times delta t. This will get useful once we start trying to establish the definite integral. For the moment, we can leave that, we can pay less attention to that last line. Let's do another example. The velocity of a particle traveling along the x-axis is given by the function v of t equals 50 minus t squared. Estimate the distance traveled from t equals 3 to t equals 5 using 8 subintervals and write endpoints. So first, let's get the width of each subinterval. It's going to be the total width of the interval from 3 to 5 divided by the number of pieces. So 5 minus 3 over 8, more 0.25. Then let's write down the right-hand endpoints of all our different intervals. Again, we start at the leftmost endpoint, t equals 3, and move over by delta t to get to the end of the first subinterval. Then we move over by delta t again and again and again to get these right-hand endpoints. Now we approximate the total distance traveled using rate times time plus rate times time plus rate times time. The rate on each subinterval is v evaluated at that right-hand endpoint. And again, here I've factored out the delta t of 0.25. Simplifying all of this, we get about 65.31 units.